Welcome to our deep dive today. We're going to be exploring some excerpts from Asher Perez's book, Quantum Theory, Concepts and Methods. It's, no, it's a pretty intense physics-focused look at quantum mechanics, so get ready to challenge some of those classical assumptions you might have about how the world works.
Yeah, Perez really wants us to understand quantum mechanics like from the ground up, by focusing on what physicists actually do in the lab. He calls this the operational approach.
So instead of getting lost in like all the abstract equations and stuff, he's grounding everything in like real-world experiments. I like that.
Exactly. He talks about preparations and tests. A preparation is essentially how we set up a quantum system in a specific state. And a test is how we measure or observe what happens to that system.
Okay, that makes sense. So it's all about what we can actually do with quantum systems, not just theoretical musings.
Precisely. And it leads to some really interesting insights. Take the Stern-Gerlach experiment, for example. Most textbooks use it to explain the concept of spin, but Perez uses it to delve into the limitations of measurement and the idea of completeness in quantum mechanics.
Oh, I remember the Stern-Gerlach experiment, shooting silver atoms through a magnetic field, right?
Yes. And what Perez emphasizes is that when you measure one component of angular momentum, like the spin along a particular axis, you fundamentally change the other components. It's not just an experimental limitation, it's a built-in feature of the quantum world.
So even with a perfect setup, we can't know everything about a quantum system at once. That already challenges our classical intuition about how measurements should work.
Absolutely. And to drive this point home, Perez uses some pretty vivid illustrations. Remember plate 1 in the book? It's a diagram of this intricate contraption, almost like something out of a Rube Goldberg machine that Bohr designed.
Wait, I think I remember that. It's supposed to measure the time a photon escapes from a box, right?
Yeah. Exactly. But what Perez shows is that even with this elaborate setup, there's a fundamental uncertainty in that measurement. You can analyze the spring balance in the diagram, and you'll find that the uncertainty in the photon's energy is linked to the uncertainty in the time it escapes.
So it's like there's a built-in blurriness in the quantum world, no matter how clever we are with our experiments.
That's a great way to put it. And this leads us to another key theme in Perez's book, the embrace of randomness.
Okay, I've heard a lot about the randomness of quantum mechanics. Is Perez saying it's not just about our lack of knowledge, but that the information literally doesn't exist until we make a measurement?
That's exactly right. He argues that accepting randomness as a fundamental aspect of nature is key to understanding quantum mechanics. It's not just that we don't know something, it's that the information isn't there until we force the universe to reveal it.
That's a pretty radical departure from our classical intuition. Do you have an example of how he demonstrates this idea?
He uses this really cool thought experiment in exercise 1.1. It involves sending photons through a series of calcite crystals, each tilted at a slightly different angle.
Okay, I can picture that. What happens?
Well, with one crystal, you can pretty much predict which path a photon will take. It seems deterministic. But as you add more crystals, something fascinating happens. The possible paths for the photons multiply, and the outcome becomes increasingly random. Even if you know the exact setup of the experiment, you can't predict with certainty which path a single photon will choose.
So the more we try to control the situation, the more randomness emerges. That's pretty counterintuitive.
Exactly, and this leads to a really profound question that Perez wants us to ponder. Can we ever fully predict individual events in the quantum world, or are probabilities the best we can hope for?
That's a question that gets to the heart of how we understand the universe, isn't it? Are we just fundamentally limited in what we can know?
It's a deep philosophical question, and one that Perez doesn't shy away from. And this focus on the fundamental nature of reality ties into another fascinating concept he explores, the idea of whether microscopic objects truly exist in the way we typically think about objects.
Okay, I'm intrigued. Tell me more about that.
Well, Perez wants us to be very careful about how we use language when talking about the quantum world. For example, he takes something seemingly straightforward, like polarized light, and breaks it down in terms of individual photons. He shows that our everyday language isn't quite equipped to describe what's happening at the quantum level.
Can you give me a specific example of what you mean?
Absolutely. He uses a thought experiment in figure 1.4 where we have these two beams of light with opposite polarizations that are overlapping. He asks us to imagine analyzing this light with a thick crystal. And what you find is that you can't just think of it as a simple mixture of photons with X and Y polarizations. It's much more nuanced than that.
So it's like trying to describe a symphony orchestra by listing the individual instruments. You lose the richness and complexity of the whole?
That's a fantastic analogy. Paris is really challenging us to reconsider if microscopic objects exist in the way we normally think about objects, or if they're just a convenient way of making sense of the experimental results we observe.
It's a bit like asking, does an electron really exist, or is it just a really useful story we tell ourselves? That's a pretty mind-blowing concept.
It is, and he draws this fascinating parallel to Gauss's analogy about straight lines. We use straight lines in geometry all the time, but in reality, there's no such thing as a perfectly straight line in the physical world. Light rays bend, space is curved. But the concept of a straight line is still incredibly useful for calculations and for understanding geometry.
I see where it's going with this. We can't necessarily point to a photon and say, there it is, but the concept is still crucial for explaining how light behaves in the quantum world.
Exactly. It highlights the importance of what Paris calls operational definitions in quantum mechanics. He's all about focusing on the actions we can perform in the lab, those preparations and tests we talked about, rather than getting bogged down in abstract mathematical descriptions.
So it's about grounding our understanding in what we can actually observe and measure, which brings us back to that idea of connecting the abstract math to real-world experiments, right?
Absolutely. Paris emphasizes the importance of the quantum expectation rule, which might sound intimidating, but it's actually the bridge between those abstract mathematical formulas and the world we can observe.
Okay, break that down for me a bit. What does the quantum expectation rule actually tell us?
Well, it essentially allows us to determine the quantum state of a system by measuring probabilities. So instead of saying, here's the exact state of this electron, we're saying, here are the probabilities of getting certain results if we measure its position, momentum, or other properties.
So it's like acknowledging that we can't know everything for sure, but we can still make predictions based on probabilities. And that's where figure 4.1 comes in, right?
Yes. He uses figure 4.1, which shows the distribution of magnetic moment measurements in a Stern-Gerlach experiment to visually represent how these probabilities manifest in real-world experiments. You can actually see how the results cluster around certain values, reflecting the probabilistic nature of quantum measurements.
That's a really helpful way to see how the abstract math translates into something tangible in the lab. And speaking of things that could be difficult to grasp, this feels like a good segue into the concept of uncertainty, right?
Absolutely. Peres is very careful about how he treats uncertainty relations, making it clear that quantum uncertainty isn't just about the limitations of our measuring devices.
So it's not that we just need better instruments.
Precisely. Even if we had perfectly precise instruments, the probabilistic nature of quantum mechanics would still lead to uncertainty in the outcomes. He argues that it's baked into the fabric of reality itself.
Okay, that's a pretty radical idea. Can you give me an example to illustrate that?
Imagine trying to measure both the position and momentum of an electron simultaneously. Even with ideal instruments, you'll inevitably encounter a fundamental limit to how precisely you can know both values at the same time. It's like there's an inherent fuzziness built into the quantum world.
Wow, that's really making me rethink how the world works at the quantum level. So we've been talking about single particles, but I know things get even more complex when we start considering systems made up of multiple particles, right? Where does Peres take us from here?
That's right. Peres goes on to explore the fascinating and often mind-boggling world of composite systems, where multiple quantum systems are considered together. And this is where we encounter one of the most bizarre and counterintuitive concepts in all of quantum mechanics: entanglement.
Okay, I'm ready to dive into that. Let's unpack entanglement in the next part of our deep dive.
So we left off talking about composite systems, where we have multiple quantum particles interacting with each other. This is where things get really interesting, because it leads us into this strange world of entanglement.
Okay, entanglement. I've heard that term thrown around a lot, and it always seems, I don't know, shrouded in mystery.
Yeah.
How does Perry approach this concept?
He describes it in a way that highlights just how different it is from anything we experience in our everyday, classical world. Imagine two particles, right, that are linked in a way that the outcome of measuring one is always correlated with the outcome of measuring the other, no matter how far apart they are.
Wait, so if I measure the spin of one particle here on Earth and it's up, the other particle, even if it's light years away, will instantly have the opposite spin, down.
That's the basic idea. It's like they're sharing some secret code that transcends distance. And Perry's doesn't just throw this out as some kind of theoretical curiosity.
Right.
He walks us through how we can actually create and study entangled particles in the lab.
That's amazing. So it's not just a theoretical idea, it's something we can actually observe and experiment with.
Exactly. For instance, in Figure 5.2, he describes an experiment with two calcite crystals that are used to analyze the entangled state of two photons. Even when the photons are separated, the outcome of measuring one is inextricably linked to the outcome of measuring the other.
So it's like, even though they're physically separated, they're still connected in this bizarre quantum way.
It is bizarre, and it really challenged some of the greatest minds in physics, including Einstein. He famously called it spooky action at a distance because it seemed to violate his principle of locality, the idea that objects can only be directly influenced by their immediate surroundings.
So this spooky action, it's not just some theoretical quirk. It has real, measurable consequences that have been confirmed, time again in experiments.
Exactly. And it's not just fascinating from a fundamental physics standpoint. Entanglement also has this incredible potential for practical applications, especially in the field of quantum information.
Ooh, like what?
Well, one of the most promising applications is quantum cryptography. Imagine being able to send messages that are completely unbreakable because the act of trying to intercept the message would actually change it, alerting the sender and receiver.
So it's like having a secret handshake that's impossible to fake.
Exactly. And that's what quantum cryptography aims to do using entangled particles. Any attempt to eavesdrop would immediately be detected because of those unique correlations between the entangled particles.
That's incredible. What else can we do with entanglement?
Another mind-blowing application is quantum teleportation. Now, before you get too excited, we're not talking about teleporting like objects, like in Star Trek.
Oh, darn.
It's more about transferring the quantum state of a particle from one location to another. Imagine sending a blueprint for a perfect copy rather than the original itself.
Okay, I'll take it. Still pretty amazing. And Perez explains how this is actually possible using entanglement.
He does. It involves creating an entangled pair of particles, separating them, and then using one of the particles to interact with the particle whose state we want to teleport. By measuring the entangled particles, we can transmit information about the original particle state to a distant location, allowing someone to recreate an identical particle.
So we're not teleporting matter, but we are teleporting information, which allows us to recreate a perfect replica of the original particle's quantum state. That's still pretty mind-blowing.
It is. And it's just one example of how entanglement is revolutionizing our understanding of information, computation, and even the nature of reality itself.
All this talk about entanglement and the strangeness of quantum mechanics is making me wonder about those famous thought experiments that try to illustrate these concepts. Like Schrodinger's cat. Does Perez weigh in on that at all?
He does. And he argues that the Schrodinger's cat thought experiment, while thought-provoking, is based on a misunderstanding of what measurement really means in quantum mechanics. He emphasizes that the cat, being a macroscopic object, is constantly interacting with its environment, even inside the box. Those interactions are essentially measuring the cat's state all the time.
So the environment is constantly collapsing the wave function, so to speak, preventing the cat from actually being in a true superposition of dead and alive.
Exactly. Barris points out that we need to move away from this idea of measurement as some kind of special supernatural event that's separate from the normal laws of physics.
So no magic wands involved.
No magic wands. Measurement is a physical process, just like any other interaction in the quantum world. It involves ordinary matter and obeys the same quantum rules. And the environment plays a crucial role in this process.
Okay, that makes sense. But how does he explain the apparent randomness we observe in quantum measurements if everything is governed by the same laws?
He suggests that the randomness might not be inherent to the system itself, but rather a consequence of these unavoidable interactions with the environment. It's like the environment is constantly jostling the quantum dice, so to speak, making it impossible to predict with certainty which face will land up.
I like that analogy. So the environment isn't just a passive backdrop. It's an active participant in shaping how quantum systems behave.
Exactly. And this leads to another crucial insight from Perez: the importance of distinguishing between measurable and non-measurable quantities in quantum mechanics.
Okay, I'm intrigued. What's the difference?
He argues that not all mathematical quantities that we can describe correspond to physically observable properties. Some quantities are just abstract concepts that are useful for calculations, but they don't have a direct counterpart in the real world that we can measure.
So it's like the map is not the territory.
Exactly. We need to be careful not to confuse our mathematical models with the physical reality they represent. For example, in classical physics, we can measure all three components of angular momentum simultaneously. But in quantum mechanics, we can only measure one component at a time with certainty.
Right, because measuring one component inevitably affects the others, like we talked about earlier with the Stern-Gerlach experiment.
Precisely. So while we can mathematically describe all three components, only one of them can be measured with certainty at any given time. The others become inherently uncertain.
That's a great example of how quantum mechanics forces us to rethink our assumptions about what's measurable and what's not. It's not just about limitations in our instruments, it's about the fundamental nature of reality at the quantum level. It seems like Perez is really trying to guide us towards a new way of thinking about the relationship between the quantum world and the classical world that we experience every day. Where does he take us next in our journey?
Well, building on this idea of measurable and non-measurable quantities, Perez dives into two powerful mathematical theorems that have profound implications for how we understand quantum mechanics: Gleason's theorem and the Cochin-Specker theorem.
Okay, those sound pretty intimidating. Can you break them down for me in a way that doesn't require a PhD in physics?
I'll do my best. Let's start with Gleason's theorem. Imagine quantum mechanics as this giant puzzle. Gleason's theorem is like finding that crucial corner piece that makes everything fit together perfectly. It tells us that the rules of quantum probability, which can seem very strange and counterintuitive at times, aren't just arbitrary. They have this deep mathematical consistency.
So it's like a mathematical safety net ensuring that all these weird quantum probabilities actually make sense.
Exactly. But it also has a deeper implication. It sets strict limits on how we can assign probabilities to quantum events. And this leads to the realization that quantum mechanics operates with a fundamentally different type of probability theory than the classical one we're used to in our everyday lives. It's not just about rolling dice or flipping coins. It's a whole new ballgame.
Okay, that's pretty mind-blowing. But what about this Cochin-Specker theorem? How does that fit into the puzzle?
The Cochin-Specker theorem takes this idea even further and delivers another blow to our classical intuition. It challenges this notion that quantum observables have pre-existing values before we measure them.
So it's not just that we don't know the value until we measure it, but that the value might not even exist until we make the measurement.
That's the essence of it. It's as if the act of measurement itself plays a role in shaping reality.
Wow, that's really making me question everything I thought I knew about how the world works.
Hmm.
Does Perry's offer any examples of how we can test these seemingly outlandish ideas?
He does. For instance, with the Cochin-Specker theorem, he uses the example of a spin-1 particle and a series of carefully designed filters. What you find is that the results you get depend on the order in which you make the measurements. It's like saying the path you take through the quantum forest determines the scenery you encounter along the way.
That's a great analogy. And to think, we haven't even scratched the surface of Perry's exploration of measurement in quantum mechanics. I'm ready to dive into that in the final part of our deep dive.
Okay, so we've been on quite a journey, exploring some really mind-bending concepts in quantum mechanics. We've talked about uncertainty, entanglement, and how the act of measurement itself can, shape reality. Where does Perez take us in this final part of our deep dive?
Well, having challenged so many of our classical assumptions, Perez turns his attention to this question. The question that has been haunting physicists since the early days of quantum theory. What does it really mean to make a measurement in quantum mechanics? It's the mystery at the heart of it all, isn't it? The whole idea of wave function collapse and how a quantum system goes from this blurry, probabilistic state to a definite outcome.
Yeah, and Perez tackles this head on, offering a fresh perspective that moves beyond some of the traditional interpretations. He starts by introducing this fascinating idea of pointer states.
Pointer states. Okay, I'm all ears.
Think of a compass needle.
Right.
It has this preferred orientation. It points north, and that orientation is remarkably stable, even if you jostle it a bit. It's as if the environment itself helps to maintain that alignment.
So it's like the compass needle is, I don't know, choosing a particular state and sticking with it.
In a way, yes. And that's what Perez means by pointer states. They're states of a macroscopic system that are exceptionally robust against environmental noise. They're the states that kind of win out, so to speak, in the constant interplay between a system and its surroundings.
So even though the compass needle is made up of billions of tiny particles, each behaving according to these quantum rules, the needle as a whole settles into this stable, classical-like state.
Exactly. It's a beautiful example of how macroscopic systems, which are ultimately composed of quantum constituents, can exhibit the kind of predictable behavior we're used to in the classical world.
I'm starting to see where this is going. How do these pointer states relate back to the idea of measurement in quantum mechanics?
Well, imagine a measuring device, like a photon detector. It's a macroscopic object, but it's designed to interact with a quantum system, like a single photon.
And because the detector is macroscopic, it's subject to those same environmental influences that create pointer states.
Precisely. So when the detector interacts with a photon, it's essentially choosing a particular pointer state based on that interaction. And that pointer state corresponds to the outcome of the measurement. Whether the photon was present or not, for example.
So the environment isn't just a source of noise or interference, it's actually an active participant in the measurement process.
Exactly. It helps to select and stabilize a particular outcome, making it robust and observable to us. It's a really profound shift in perspective, recognizing that the boundary between the quantum world and the classical world isn't as clear-cut as we once thought.
It's like the environment is constantly nudging quantum systems towards classicality. It makes me think of that quote, "No man is an island." Maybe no quantum system is truly isolated either.
That's a fantastic way to put it. And this leads to Perez's definition of a classical system.
Okay, I'm curious to hear this. How can we define classical in a world that's fundamentally quantum?
He says that a classical system is one where all measurable quantities commute.
Can you unpack that a bit? What does it mean for quantities to, like, commute?
In essence, it means that we can measure those quantities without affecting each other. So all the things we can observe about a classical system can have definite values at the same time. There's no inherent uncertainty or fuzziness in our knowledge of the system's properties.
So it's the world of billiard balls and planets, where things behave in predictable, deterministic ways, at least from our macroscopic perspective.
Exactly. But of course, we know that even these seemingly classical systems are ultimately made up of quantum particles. And that's the beauty of Perez's approach. He recognizes that classicality is not an inherent property of a system, but rather a matter of perspective.
So it depends on what we choose to measure and how we interact with the system. It's like zooming out from the quantum world and seeing the familiar patterns of classical physics emerge.
Precisely. It's about recognizing the different levels of description that are appropriate for different scales and situations.
Okay, I think I'm starting to wrap my head around that. It's a pretty elegant way to reconcile the strangeness of quantum mechanics with the world we experience every day. This whole discussion is making me think back to that mind-bending thought experiment, Schrödinger's cat. Does Perez offer any insights on how we should think about that paradox in light of these ideas?
He does, and he argues that the Schrödinger's cat thought experiment, while intriguing, is based on a misunderstanding of what measurement really means. Remember, he's emphasizing that measurement is a physical process, not some kind of mystical event.
Right, and he's saying that the environment plays a crucial role in this process.
Exactly. The cat, being a macroscopic object, is constantly interacting with its environment. Even inside that infamous box, those interactions are essentially measuring the cat's state all the time.
So those interactions are constantly collapsing the wave function, so to speak, preventing the cat from actually being in a true superposition of dead and alive. Like the environment is constantly taking snapshots of the cat, so it never has a chance to be in that blurry quantum state.
That's a great way to think about it. The cat state is constantly being nudged towards classicality by its interactions with the surrounding air molecules, the walls of the box, and so on. So there's no need to invoke this mysterious collapse of the wave function when we open the box. The apparent collapse is simply a consequence of the cat's inevitable entanglement with its environment.
It seems like Perez is really encouraging us to move beyond the simplistic picture of measurement as this separate mystical act, and to embrace this idea that it's an integral part of the physical world, governed by the same laws as any other interaction.
That's exactly right. And I think the biggest takeaway from Perez's work is that quantum mechanics is not just a collection of abstract mathematical formulas. It's a description of the world we live in, a world that is both strange and beautiful, full of wonder and possibility.
And Perez, with his clear thinking, his insightful analogies, and his infectious enthusiasm, shows us how to navigate this extraordinary landscape. He encourages us to embrace the mysteries and challenge our assumptions about the nature of reality itself.
He invites us to continue the journey of exploration, to ask new questions, and to push the boundaries of our understanding. For in the quantum realm, the adventure is just beginning.
Well said. And on that inspiring note, We'll wrap up our deep dive into Asher Perez's insightful work. We've covered a lot of ground, from the operational meaning of measurement to the mind-bending concepts of entanglement and the role of the environment in shaping quantum reality.
It's been a fascinating journey, and I hope our listeners come away with a deeper appreciation for the beauty and the strangeness of the quantum world.
Absolutely. Thanks for joining us on this deep dive, and keep those minds open to the wonders of quantum mechanics.